speaker in this session is Dr. Kriti Goel from IIT Gandhinagar, a name which all of us are familiar, particularly with the most of us are part of the ongoing commutative algebra seminar from IIT Bombay, and she is a key organizer of that. She was in IIT Bombay prior to joining IIT Gandhinagar. So she will speak on row-factorization matrices and generic ideals. So start, Kriti.
Thank you, Professor Datta. It's my pleasure to talk today, first of all, on this occasion of superannuation of Professor Dilip Patil. I met him a few years back at an advanced instruction school. I was a student then. And of course, throughout the years after that meeting, I just not have been his student, but I've also been his tutor in several of the courses, and all of these experiences have been equally enriching. I have learned a lot from him, and I just wish him all the best of his health, and I just hope he continues to inspire a lot more students into this beautiful world of mathematics. So today I'll be talking about row-factorization matrices and generic ideals. This is a joint work with Prakash, Bhardwaj and Indranath Sengupta. So of course, I'll be talking about numerical semigroups, which was a well talked about topic yesterday, thanks to talks of Professor Herzog and Professor Sengupta. So today I'll take this liberty of just picking up a few definitions, which I wish to recall. Just for today's lecture, I will not dig deep into the essence of numerical semigroups, but just touch upon a few definitions, which I will need. So of course, starting with the numerical semigroups, of course, we'll be assuming that these semigroups are finitely generated. This means we are picking up S elements n1 up till ns over the natural numbers such that their common GCD is equal to 1. And by a numerical semigroup, we mean an additive submonoid generated by these S elements n1 up till ns. Of course, an equivalent way of characterizing numerical semigroups is looking at this complement set, which is called as a cap set. This is complement of the semigroup inside the set of natural numbers. And the way we characterize numerical semigroups is by the finiteness of this cap set. And since we have this cap set, which is finite, this means we can talk about the maximum element of this cap set. And this is what is called as the Frobenius number, which is associated to this numerical semigroup. Of course, the other way of saying this as a Frobenius number is that beyond the Frobenius number, every natural number is an element of a numerical semigroup. The next term we define is the pseudo-Frobenius number. Of course, these elements again are picked up from the cap set, but now they satisfy the property that these elements, which are I'm denoting by F, they should satisfy the property that F plus any non-zero element of the numerical semigroup should land inside the numerical semigroup. Of course, Frobenius number satisfies this property just by the definition. And by the collection of pseudo-Frobenius numbers, we have the set which we denote by PFH. So there's a connection between studying pseudo-Frobenius numbers and properties of numerical semigroups. One such small connection is the definition of symmetric numerical semigroups. Of course, there are various ways to define it, but one of the important characterizations of symmetric numerical semigroups is via the cardinality of the set of pseudo-Frobenius numbers. So we say that H is a symmetric numerical semigroup if and only if we have the Frobenius number to be the only pseudo-Frobenius number in the set. And of course, the other object that we associate with the numerical semigroups is the semigroup ring. This is the algebraic association of this so-called combinatorial object. So what is a semigroup ring which we can associate? So let's say we have a field K. Then the semigroup ring, which we denote by KH, is a subring of a polynomial ring. And it's generated by the monomials of the form t to the power h, where h varies over the elements of the semigroup. And of course, since we are associating an algebraic object with our semigroup, one would want to have this association so that we can study properties of semigroup in terms of the ring and vice versa. So one of this beautiful connection was made by Kunz in 1970, in which he proved that we have a symmetric numerical semigroup if and only if we have the Gorenstein property for the corresponding semigroup ring. And we have already seen that by symmetricity of the numerical semigroup, we have that the cardinality of the set of pseudo-Frobenius numbers is exactly equal to 1. So indeed, pseudo-Frobenius numbers in the background do play a role in characterizing certain properties of the numerical semigroups. So let's dig more deep into them. So the other equivalent way of defining pseudo-Frobenius numbers is the following. Of course, we pick these elements from the gap set, but equivalently, one can define them in a way, in the following way, that we have this element f from the gap set which satisfies the property that f plus any of the generator of the numerical semigroup should be an element of the numerical semigroup. So instead of imposing this condition on every non-zero element, it's equivalent to have this condition on the entire set of generating set of the numerical semigroup. So we had n1 up till ns, so we had s generators. This means this equation, this condition rather, f plus ni being an element of H, gives us a set of S equations in S number of variables. And as soon as we have the setup of S equations, S number of variables, we can always go back to matrices. And this is what the idea that was picked up by Moscariello in 2016. Given a pseudo-Frobenius number, he associated an S crosses matrix with it using the above definition. So let's go through this. So we have a pseudo-Frobenius number f, and to this we associate an S crosses matrix, which he called as a row-factorization matrix, such that when we look at the ith row of this matrix, this is really a factorization of f plus ni. And if one really looks at this matrix, this means we have the diagonal entries of this matrix to be -1, and all the other entries of this matrix are just natural numbers. Of course, we just have to make sure that the ith row is the factorization of f plus ni. And of course, as I say, it's a factorization of f plus ni as a linear combination of the other generators of the numerical semigroup. This factorization may not be unique. So given a pseudo-Frobenius number, we may be able to associate a number of row factorization matrices depending on how many factorizations of f plus ni for each I we are able to make. Of course, I'll also give an example of the same, but once we have the setup of row factorization matrices, what can we do with it? And of course, since Moscariello defined it, what was the thing that he could prove using this kind of tool or technique? And this is very interesting because something which is as simple as matrices could help him prove the following theorem. He proved that the Cohen-Macaulay type of an almost Cohenstein monomial curve in A4 is at most 3. And in other words, if I want to interpret this in the language of numerical semigroups, it just says that for an almost symmetric numerical semigroup, H, which is generated by 4 elements, the cardinality of the set of pseudo-Frobenius numbers is at most 3. And just to quickly recall what is an almost symmetric numerical semigroup, this just means that if we pick up any pseudo-Frobenius number, which is of course not the Frobenius number, then the Frobenius number minus this f is also pseudo-Frobenius number. Just a quick definition of almost symmetric numerical semigroups. But a theorem which seems to be as involved as this, Moscariello was able to prove it using row factorization matrices. And if one really looks at the proof, what is more interesting that he just counts the number of zeros which are inside these matrices for various pseudo-Frobenius numbers, and then he's able to come up with this kind of result. So row factorization matrices do have in them embedded a lot more information about about the numerical semigroups, and we'll see a few more connections, of course, later. But before that, let's just quickly look at an example. So I'll just pick up a simple example. We have a numerical semigroup generated by 3 elements, 5, 6, and 9. When we look at the gap set, it's just these elements 1, 2, 3, 4, then 7, 8, 10, 11, 12, of course, they are there in the numerical semigroup. The next gap is 13. And beyond 13, every other natural number is an element of our numerical semigroup. And one can check just by the definition that 13 is a pseudo-Frobenius number. Of course, 8 is not, because 8 plus 5 is 13, which is in the gap set. And similarly for the other numbers, like 7 plus 6 is 13, which is there in the gap set. 4 plus 9 is 13, which is in the gap set, and so on. So 13 is indeed our pseudo-Frobenius number. This means we have to look at the 3 equations, 13 plus 5, 13 plus 6, 13 plus 9, write them as an n-linear combination of the other generators of a numerical semigroup. So while 13 plus 6 and 13 plus 9 have unique factorizations in terms of 5 and 6 and 9, when we look at 13 plus 5, it's 18. It can be written as 3 times 6. It can also be written as 2 times 9. And this gives us two possibilities of Row-Factorization matrices, which can be associated to our pseudo-Frobenius number 13. So just a quick example of seeing the connection of pseudo-Frobenius numbers with Row-Factorization matrices. Next, I'll talk about this very particular class of numerical semigroups, which are generated by almost arithmetic sequence. This was also hinted upon yesterday by the two talks, but I'll quickly recall it. So what do we mean by an almost arithmetic sequence? So of course, we'll begin with an arithmetic sequence. So let's say we have this strictly increasing arithmetic sequence, M0, M1 up till MP. To make it almost arithmetic sequence, we add an extra natural number, which just satisfies this property that now the GCD of this entire sequence, M0 up till MP, and the new natural number we added is equal to 1. And of course, we also have to make sure that this sequence forms a minimal generating set for our numerical semigroup H. So this numerical semigroup H is what is called as a numerical semigroup minimally generated by an almost arithmetic sequence. So these semigroups were actually studied very deeply by Professor Patil and Professor Balwant Singh in 1990. And this paper really led to a series of papers where they proved a lot many things about this class of numerical semigroups. I'll just state the ones which I'll require. The first one being the paper by Professor Patil in 1993, where so there's this very technical setup which is given by Patil and Singh in 1990, which is associated to this class of numerical semigroups, but the setup may sound too technical when one sees it, but this setup turns out to be so much useful and powerful that the authors were able to find a lot more properties and a lot more information about the semigroups using that setup. Of course, the two main things were finding the minimal generating set of the defining ideal. This was a paper in 93. And the other information that they could gather was about the pseudo-Frobenius numbers. They could actually give a complete description of the pseudo-Frobenius numbers using that so-called technical setup. So this description was in 1999 by Patil and Sengupta. And if one wants to look at Row-Factorization matrices now, which can be associated to this class of numerical semigroups. So the very first step is we need the information about the pseudo-Frobenius numbers. And this is what we could gain from this paper of 99. So using this information of pseudo-Frobenius numbers and the so-called technical but very important setup in the paper of 1990, we were able to actually give a complete description of the Row-Factorization matrices. Of course, it's a little technical, and since we have this generating set for our numerical semigroup, which is generated by P plus 2 elements, this means the matrices are indeed huge, P plus 2 cross P plus 2. So in the interest of time, I guess I'll just rest with the fact that we were able to give a complete description of the matrices rather than giving you a complete picture of it. But what is more important here is what we can decipher now from this information. Once we have a complete description of the matrices, what information can we dig out more about these class of semigroups? And this is what brings us to the next topic of generic toric ideals. So I'll quickly recall what these are. So of course, in the beginning, I mentioned that if we have a numerical semigroup, we can associate a semigroup ring to it. The way we saw it was as a subring of a polynomial ring. The other way to see this ring is by looking at it as a quotient of a polynomial ring. And when we look at this quotiented ideal, this is what is called as the defining ideal of the semigroup ring, or the relation ideal, as it was said yesterday. So defining ideal or the relation ideal of the semigroup H. This ideal is a toric ideal and is generated by binomials. And this term of generic toric ideals, this was coined by Piva and Strumfels in 98. And the way they defined it is as follows. So if a toric ideal has a minimal generating set which consists of binomials with full support, that's how they defined it to be called as a generic toric ideal. We just need one minimal generating set which consists of binomials having full support. And why is it important to study such kind of or such class of toric ideals? they proved in the same paper that if we have a generic toric ideal, IH, then when we look at the corresponding semigroup ring, it is colored. And as a consequence, they were able to prove that this, as a consequence, says that the Poincare series of the residue field is rational. So this is a good enough reason to study more and more about generic toric ideals. So we have Row-Factorization matrices associated to a semigroup. We have generic toric ideals, a special kind of condition for toric ideals in the semigroup rings. Is there a way to connect these two properties? And this connection was made by Ito in 2020, where he proved that the defining ideal is generic if and only if for every pseudo-Frobenius number, it has a unique Row-Factorization matrix. And we also have the property that given any column of this matrix, all the row entries of that particular column are distinct. So these two properties were necessary and sufficient for characterizing the generic nature of the toric ideal. And this really beautifully connects the factorization matrices with the defining ideal. And so let's just quickly look at the example we saw in the beginning. We have a numerical semigroup generated by 5, 6, and 9. We saw that the Frobenius number, the pseudo-Frobenius number here is 13. And we saw two different Row-Factorization matrices which could be associated to that pseudo-Frobenius number. And by the result of E2, it kind of says that since we do not have a uniqueness in particular, it should say that we do not have the generic nature of the toric ideal. And this is indeed true when we look at this semigroup ring as a quotient of the polynomial ring. This is what we get. The defining ideal is generated by y cube minus z square and x cube minus yz. And indeed, when we look at the first binomial, y cube minus z square, it's not a full support. So just a quick example to put things into picture. So once now we have this connection, which was built up by Ito, and then we had a complete description of Row-Factorization matrices for numerical semigroups which were generated by an almost arithmetic sequence. The next question was, can we build up this connection in this particular class as well? So if we have a numerical semigroup which is minimally generated by an almost arithmetic sequence, we have an information about the Row-Factorization matrices. Using this result of Ito and the information, we could prove the following result. First of all, it says that if P is equal to 0, in particular, if we have a generating set of two elements, then IH is generic. It's kind of known. If we have P equal to 1, then under some technical setup, we have that the defining ideal is generic. Otherwise, it is never. So this is the class of rings where it's generated by 3 elements. The last thing we prove is that if we have P strictly bigger than 1, in particular, if the embedding dimension is strictly bigger than 3, then we prove that in the case of the special class of numerical semigroups, the defining ideal of the semigroup ring is never a generic toric ideal. Of course, the other result which we prove is for the numerical semigroups which are complete intersection, in particular, the numerical semigroups whose semigroup ring is a complete intersection. And we prove the following. So if we have a semigroup, which is a complete intersection numerical semigroup, it has embedding dimension at least 3, then we prove that the defining ideal is never a generic toric. So this is one information which in generality we could say about complete intersection numerical semigroups. So next, apart from this connection of Row-Factorization matrices with the generic toric ideal, there's also the other relation, which is the other connection between matrices and the defining ideal, which is given by certain binomials. These binomials are what are called as RF relations. So if we have a numerical semigroup and a pseudo-Frobenius number, we have a Row-Factorization matrix. So let delta 1 up till delta S denote the row vectors of the Row-Factorization matrix, which is an S cross S matrix. So we have these S row vectors, and by delta ij, we denote the difference of the jth row with the ith row.
Sorry, did it get frozen or?
I think she's back, yeah.
You are muted, Kriti.
Yes, yeah, I didn't realize when I lost the connection. Can you please help me where I lost it? Hello? Am I audible?
Start with the slides, RF relations. RF relations.
Okay. Okay, thank you.
Can you, RF relations.
Okay, sir, thank you. Okay, so there's, of course, another way of connecting row-factorization matrices with the defining ideal. This is via certain binomials, which we call as RF relations. So that's how we define them. So let's say we have this numerical semigroup H, and we have a pseudo-Frobenius number F. And of course, to the pseudo-Frobenius number, we have associated a row-factorization matrix, which is an S cross S matrix. So let delta 1 up till delta S denote the row vectors of this matrix. By delta ij, we denote the difference of two row vectors, delta j and delta I. So now once we have this row vector delta ij, which is a difference of two row vectors, we'll have certain positive components of this vector and certain negative components. So we separate them out. So delta plus ij denotes the vector which has all the positive entries of delta ij. And delta minus is the vector which corresponds to the absolute value of the negative entries of delta ij. And with this two vectors separated, delta plus and delta minus, we can form this particular binomial phi ij, which is x to the power delta plus minus x to the power delta minus. And just by the definition of it, one can easily check that these kind of binomials do land inside the defining ideal. And these binomials are what we call as RF relations because they come from the row-factorization matrix of the pseudo-Frobenius number F. So given a binomial F in the defining ideal, we say it's an RF relation if it is RF-F relation for some pseudo-Frobenius number. And of course, this gives us an idea that these binomials they are indeed elements of the defining ideal. So the next question is, which was raised by Watanabe and Herzog, is that when can IH be minimally generated by these binomials, which we call as RF relations? You know, these elements are indeed elements of the defining ideal, but when do they become a minimal generating set for this defining ideal? Of course, they also proved it in certain cases, precisely when embedding dimension is equal to 3, and the other cases when embedding dimension is 4, but the numerical semigroup has extra properties where it is either almost symmetric or it is pseudo-symmetric. So the reason we answer it is, and the way we answer it is the following. So the setup is, again, we come back to numerical semigroups generated by an almost arithmetic sequence, but now we restrict ourselves to the condition of the semigroup being symmetric. And we also impose this condition that embedding dimension is either 4 or 5. So under this setup, we were able to prove, using the information from the row-factorization matrices, that the defining ideal has a minimal generating set which consists of RF relations. So in embedding dimension 4 or 5, under the condition of symmetricity, we were able to prove that for this class, the question indeed has an affirmative answer. So this was really the story about numerical semigroups. This means we are over the space of natural numbers. So this means the next question one can ask is, what happens over high dimensional spaces? Can this story be said over high spaces? And this is what I would like to touch upon in the last part of my talk. This is still an ongoing work, but I thought it's better to complete the story in high spaces as well. So what do we mean by, first of all, semigroups in ND? So of course, to begin with, our semigroups are finitely generated. So over here, we are looking for finitely generated submonoids of ND. Let's say they're generated by N1 up till NS. And this is what we'll call as the affine semigroups in high dimensional spaces. The next step is to look for the gap set. Over the set of natural numbers, our gap set was just the complement of the semigroup in the set of natural numbers. But over ND, there's not one natural choice that one can pick. So over here, what we do is we look for the complement of the semigroup inside its group. So let GS inside ZD denote the group generated by this affine semigroup. By gamma S, which we call as the gap set, this is complement of S and GS, and then we are just only restricting ourselves to ND. And then in this particular gap space or the negative space, we can now have a parallel definition for pseudo-Frobenius elements. These are again the elements from the gap set defining, satisfying the property that F plus Nj is an element of S for every J. So of course, when we are talking about high dimensional spaces, as I said about gap set, things don't follow parallelly, and there are more things which can fall apart when we talk about high dimensional spaces. The next hurdle being that, of course, we were able to define the set of pseudo-Frobenius elements, but what is it that kind of confirms that this set will be non-empty? We should first of all prove the existence of such kind of elements. And in order to prove the existence, we have to firstly define what are called as MPDs, or semigroups which have maximal projective dimension. So we say S has maximum projective dimension if, when we look at the corresponding semigroup ring, the projective dimension of the semigroup ring is S minus 1, or equivalently, we have depth to be equal to 1. And then it was proved by Garcia and of course a few more people in 2020 that the condition of the set of pseudo-Frobenius elements being non-empty is equivalent to saying that our semigroup is MPD semigroup. Of course, I would like to also mention here that the setup which this paper had was a little different from ours. The negative space they took was over the cone, but over here we thought for, of course, the later part of the talk, it was better to look at the complement set of S over its group and not the cone. So that's a slight difference between our setup and theirs, but when we look at the proof of this result, which is indeed a very nice one, the proof follows in our scenario as well. So of course, that's first observation. The second observation being that, of course, when we would want to work with pseudo-Frobenius elements, we want the set to be non-empty. This means we have to force the condition of the semigroup to be an MPD semigroup, and we do have a large class of rings which satisfy this property. But then we also lose one thing. Over the set of natural numbers, our semigroup rings were always Cohen-Macaulay because they were dimension 1 and they were domains. But if we are imposing the condition of S to being MPD semigroup in high dimensional spaces, this condition is equivalent to saying that the depth of the ring is 1. In particular, if your dimension D is bigger than or equal to 2, these rings will never be Cohen-Macaulay. So this one Cohen-Macaulay property is something that we will lose once we impose the condition on MPD, but we do have existence of pseudo-Frobenius elements, and then one can work more and try to dig in more and establish connections. Of course, the other observations are that the set is, first of all, finite, the cardinality of the pseudo-Frobenius elements. And by the cardinality, we really mean, we denote it by the type of S. Of course, it's not really the Cohen-Macaulay type, but just the type of S. And since all of the setup follows parallelly, one can also define Row-Factorization matrices parallelly here. And of course, next thing I would want to touch upon quickly after pseudo-Frobenius elements is Frobenius elements, but before that, an example that Row-Factorization matrices can really be defined in a parallel way. So we have this affine semigroup, which is generated by these 6 tuples. So this means we can form a semigroup ring R, which is quotient of this polynomial ring kx1 up till x6 over the defining ideal. This is our ks. Now, the proof of this result, which says S is MPD if and only if your pseudo-Frobenius, the set of pseudo-Frobenius elements is non-empty, actually gives a very nice construction of pseudo-Frobenius numbers using the resolution of the semigroup ring as a module over the polynomial ring. And this is the kind of construction that we'll be using here. So just a tiny observation here that when we look at the minimal free resolution of the semigroup ring, we look at the last SG. Of course, there may be many summands in here. You look at the shifts in the degrees at the very last step. Over here, we have 2 components, one having the shift as 16, 15, and the other one having the shift as 17, 18. These are the degrees of the last topmost SGs. To these tuples, the paper says that what you do is the following. You look at your generators, add them up, and then subtract this number from the degrees you obtain. So over here, first degree 16, 15. When we add up all our generators, we get the tuple 15, 12. We look at the difference. The first one says 1, 3. And then when we repeat the same process with 17, 18, we get the other tuple 2, 6. And one can check that these 2 elements are indeed pseudo-Frobenius numbers. And these are the only pseudo-Frobenius numbers which can be associated to our affine semigroup S. And now since when we have these 2 tuples, let's say we look at the Row-Factorization matrix corresponding to 1, 3. So first row will correspond to factorization of 1, 3 plus 0, 1. That's 1, 4, which is one of the generators. and hence we get the first row and so on and so forth. So of course, the construction of row-factorization matrix will follow in a parallel way as we had over the case of natural numbers, but of course, we can have a similar setup in high-dimensional spaces. So let's quickly look at the pseudo-Frobenius elements, because even they have an interesting story over high-dimensional spaces. First of all, over the set of natural numbers, we had a very unique pseudo-Frobenius element, and its existence was also guaranteed because of the complement set being finite. And all of this setup shatters when we look at high-dimensional spaces. So the way we define pseudo-Frobenius elements, which is kind of a set to begin with, is by the following way. Of course, we pick elements from the gap set which we define, and now they should satisfy the property that with respect to some term order, F should be a maximum element over our gap set. And of course, parallelly, we can define symmetric semigroups over ND, and it's just the way to define symmetric semigroups is just by two conditions. First of all, the cardinality of this set of pseudo-Frobenius elements should be 1, and we should have existence of Frobenius element. This is an extra condition as compared to the set of natural numbers, because we may not have existence of Frobenius element, which I'll just quickly say in one of the examples. So first example is S1, which is generated by these 5 tuples. This is symmetric because using the same step as before, we could look at the resolution of the semigroup ring, look at the top degree, subtract it with the difference of, subtract it with the sum of the generators. What we get is 7, 2. And 7, 2 is actually the maximum of this gap set, where this maximum, it's maximum with respect to this term order, which is the graded lexicographic order. So we do have an example of a symmetric semigroup because the cardinality of the set of pseudo-Frobenius elements is 1, and we have existence of Frobenius element. But we do have an example where the cardinality of the set of pseudo-Frobenius numbers is 1, but the existence of Frobenius element is not true. And this is what we have as an example. This is kind of really the Brzezinski curve, S2. I'll just quickly recall how it was defined. So we have a curve which is generated by 4 elements. And how it is defined for h bigger than equal to 2, we have these 4 elements, n1, n2, n3, and 4. We look at the projective closure corresponding to this monomial curve. This is generated by 0, n4, n1, n4 minus 1, n2, n4 minus n2, n3, n4 minus n3, n4, 0. So this is the affine semigroup that we look at in n2. And using the same step as above, we look at the resolution. This resolution was resolution of KS bar. This was given by Indranath, Sengupta, and few of his students very recently. We use this setup to pick out the degree shifts in the highest component. And doing the same calculation as above, we get that this F, which is given by this tuple, is a pseudo-Frobenius element. But we were able to check that in the gap set, this particular tuple does not form a maximum with respect to any term order. So indeed, this is not a Frobenius element. So this kind of says that defining symmetric semigroups may not be even as trivial as we could do it over the set of natural numbers. Of course, lastly, I would like to wind up with coming back to the same thing again, the connection of RF-matrices and generic toric ideals. We are still working on it, but the progress we have till date is that if we have an MPD semigroup, which we need to put as a condition because we want the set of pseudo-Frobenius elements to be non-empty, we are able to prove that if we know that the defining ideal is generic, then we were able to prove that for every pseudo-Frobenius element, the row-factorization matrix is unique, and given any column, all its row entries are distinct. It's just one way result as of now. We do hope for the converse also to be true, but we are still working on it. So it's a little early for that. So of course, this is one of the observations that we make as a connection. The other result is about almost symmetric semigroups. The way we define almost symmetric semigroups in the case of natural numbers, we can have a parallel definition in here as well. But of course, for everything which involves Frobenius numbers, we assume we have existence of Frobenius numbers. And once we have this, we were able to prove that if we have an affine semigroup generated by at least 4 elements, which is an almost symmetric MPD semigroup, then we are able to prove that the defining ideal is never a generic toric ideal. So these were just some set of observations that we were able to parallelly prove in the higher dimensional spaces. Of course, this is still a work in progress. And I guess with this, I'll end my talk. These are the set of references which I used in my talk. And thank you for your attention.
Okay, so yeah, so thank you. This lecture on a very interesting topic. Now, any questions, quick questions, comments? Okay, so if you don't have a question, the speaker later or maybe after the next lecture. So I think it is time for the next lecture to begin.